Now let's take a look here at part C. We're going to try to choose whether or not we want to proceed using the minutes or the hours unit of time that we established in the last video. Let's see what we have here. What is the probability that over 50 minutes will elapse between any two defects? Okay, I'm going to quickly here say that since I was given time already in minutes, why not just use the minutes side of things? So I could draw out my number line, measuring everything in terms of minutes. My distribution would look something like this, and I'm just going to say wherever 50 is on the number line, that's what I want to go over. So this should be pretty simple. I want the probability that x is bigger than 50. And I know that should be e to the negative 50, and I just have to multiply by a lambda that worked with minutes. Well, that was this one, 0.069. 0.069. So if you went to a calculator and you typed all of this in, you should end up with a final value of 0.0317. You could double check that on your own. Okay, well let's see. Part D. Should we be surprised if 10 defective units were found in a 1-hour period? Okay, we got to be careful here. If you take a look at all the previous parts in this question, we've been asking something like, how much time is going to elapse before the next defect, or between any two defects? But are we really asking about here how much time is going to pass? Not quite. In part D, we're asking a question of, should we be surprised if 10 defective items are found if the time period is fixed? Well, this is very strange. What this means is that we actually have an entirely new variable here. We could say, how about we let y represent the number of defects we find in 1 hour. Well, if we're trying to find the number of defects that we have in 1 hour, then that's not a continuous that's not a continuous distribution. That's a discrete distribution. And we could say y has specifically here a Poisson distribution. And the value of lambda should be the number of defects that I find in 1 hour. Well, fortunately for us, we already computed that value up here. Lambda is 4.14 defects per hour. So I know that that's 4.14. So now I can go ahead and compute this as the probability that y, the number of defects I find, is 10. And that's going to be a Poisson PDF with a 4.14, comma, 10. And again, if you were to go to the calculator and crunch this out, you should be able to confirm that you get a value of 0.0065. So should we be surprised if we found 10 defects? That is, would this be unusual? Well, do you remember what our cutoff for things being unusual was? Well, yeah, that would be under 5%. And this number is definitely under 5%, right? This is 0.65%. It's not even up to 1% yet. It's like a little over 0.5%. So we could say, yes, this would be surprising. It's under the 5% mark. So when we take a look at these types of questions with exponential distributions, we again need to see that this exponential distribution, which is discrete, and the Poisson distribution, which is discrete, and this exponential distribution, which is continuous, often work together with one another. They're kind of like asking the same question, but from two different directions. They're actually used a lot in areas of sometimes what's referred to as queuing theory or theory of waiting lines. It may seem strange that that's actually something that's studied, but it is, because a lot of times you want to understand how traffic flows and things like that work in different areas, so that way you can optimize certain sorts of behavior. So the Poisson distribution is used to analyze how frequently things may be arriving, right? Like how many defects do I find in a given period? How many people show up at the bank in a given amount of time? But the exponential distribution is used to measure what's often referred to as inter-arrival time. How long before the next thing comes up? How long before the next customer arrives or the next defect is found? In the next video, we'll take a look at some special properties of the exponential distribution, as well as continue to talk about this importance of changing the interval or the amount of time or the units of time that we're looking at in a given question.